Good day, respected set of panels. I am Ronnie Bikini and I'll be presenting my research entitled Identifying the Relation of Deep Well Groundwater Exploitation to Surigao City's Terrain Deformation. Outlines of these presentations are the introduction, which has the objective and significance of the study as its contents, the map of the study area, the methodology, where the process of this research is discussed, the results and discussions, the conclusions, and the recommendations. The introduction. Terrain deformation happens as Earth's geophysical appearance changes from time to time that is caused by natural phenomena and human activities like urbanization. Land subsidence is a type of terrain deformation where a gradual setting or sudden sinking of Earth's surface is happening due to removal or displacement of subsurface Earth materials like the groundwater. Anthropogenic cause of land subsidence has been a major problem in urban centers in Asia and is dependent to the locals' population increase. Surigao City as example. Different approaches are used in measuring land subsidence are used worldwide that dates back to basic leveling techniques. Due to technological advancements, satellite-based measurements are applied, and one of few examples is the application of INSAR. Sentinel INSAR is used in this study to investigate whether measurable changes in Surigao City's terrain exist and investigate whether these changes attributes that of the deep well groundwater exploitation. The objectives of the study. The main objective of this work is to identify terrain deformation in Surigao City and correlate deformed areas with the SMWD's water extraction. Significance of the study. This study produced a terrain deformation map of Surigao City. The results will help the residents of Surigao City to understand the impacts of gradual groundwater extraction and give light to possible geohazards this could cause, such as flood inundation, aggravation of flooding, and the overall effects on the aquifers to store water. These impacts which will lead to future researches. Shown here is the map of Surigao City. Located in 9 degrees 47 minutes north latitude and 125 degrees 29 minutes east longitude, Surigao City amasses 245 square kilometers that comprises 54 barangays. Average elevation is at 19 meters, with the highest at Kabangkaan Ridge at 465 meters above mean sea level and the lowest, Barangay Bitaugan, at 3 meters above mean sea level. 154,000 inhabitants are recorded in the 2015 census, and 72.7% of the city is used for agricultural and industrial use, thus the need for clean water resource. Methodology. 3 main activities were made in this research: the data acquisition, image pre-processing, and validation of processed maps. Acquired data are the sentinel satellite images, the digital elevation model, and the deep location along its dimensions. Cumulative Densar approach is used in the study using SNAP version 8.0 software. The image pair of downloaded satellite images are labeled the master image for the initial year 2017 and the slave image for the final year 2018. These images are then co-registered with the DEM so that the orbital information will be conjunction for both images. Copernicus 30 meters global DEM is the digital elevation used in the study. Interferogram is generated by cross-multiplying the master image with a complex conjugate of the slave. Aftermath of this process is the coherence images that indicates the coherency between the master and the slave image, and an interferogram that shows fringes that validates the existence of ground deformation. Topographic phase removal is where the spatial baselines are registered. Noises like temporal decorrelation, geometric decorrelation, volume scattering, and processing error in an interferogram is unavoidable, and this is where the interferogram filtering comes in. Multi-looking suppresses the noise and corrects the image's proportion, while these noise are eliminated using Goldstein filtering technique. Displacement on the interferogram are shown after the statistical cost network flow algorithm for phase unwrapping or the SNAF operator is used. This is an external processing done outside the SNAP software. Time series deformation map are then produced that shows deformation in Surigao City. These deformations are then analyzed for validation in areas where SMWD's details are situated. Results and discussions. The coherence coefficient map of Surigao City. The coherence map shows coherency on each pixel value of the satellite image pair. The higher the coherence value, the higher pixels per image matches. An average of 0.34 coherence is recorded in the coherence map, which indicates the satellite image passed the maximum allowable threshold for the Densar processing that gives certainty to other results. The highest recorded pixel coherency is at 0.97 units. The interferogram. Interferogram shows network of fringes on the image. More elaborate fringes will confirm that an actual deformation is happening in the area where the fringes are located. Notable fringes are on the northern part of the mainland area of Surigao City and on the island barangays. Terrain deformation map of Surigao City. Terrain deformation map of Surigao City is divided into 11 classes, which implies a red color for the subsiding area and blue for the uplift. Red and blue color texture gets stronger as an area gets bigger recorded subsidence and uplift, respectively. As it is shown in the map, terrain deformation at centimeter scale is evident in Surigao City between the interval of April 2017 to April 2018. Majority of Surigao City appears to be subsiding, as negative 1.47 centimeters of deformation is recorded, which is shown in the percentile where 74% of the area are subsiding and 26% are experiencing uplift. The island areas of the city shows either slight uplift or slight subsidence. Slight uplift, or the lightest blue color, is seen in the southwestern part of Barangay Talisay, the eastern part of Zaragoza, and the northeastern part of Maniagao. Slightly darker blue shade is seen in barangays Bitaugan, Sugbay, and Kagutsan. Slight subsidence, or the lightest red color, is observed in northeastern part of Barangay Talisay, Aurora, Cantiasay, and San Jose. Majority of subsidence in the mainland part of the city is expected as it is the center for urban development. Most of the northern half until the central portion of the mainland shows relatively low magnitude of subsidence, or the lightest red color, as this area is the economic center of the city. Darker shades of red that shows higher subsidence measurements are seen in the southern part of Barangay Mati and the adjacent Barangay Anomar, where the highest recorded subsidence of 14.6 centimeters is situated. The highest recorded uplift is 9.8 centimeters and is located in Barangay Kabungbungan, which is located in the most eastern part of the mainland Surigao City. Terrain deformation map on areas where SMWD's deep wells are located are added with contours to specify the elevation of the area. Terrain deformation map recorded 1.02 centimeters, 1 centimeter, and 2.58 centimeters subsidence in Poktoy 2, Poktoy 3, and Serna 2 deep wells respectively. Subsidence in the areas could be caused by the El Niño that ended 2016. It is possible that the aquifer has not yet recovered to its full recharge during its time. Low subsidence is measured in both the Poktoy deep wells. Poktoy 3 showed low subsidence even though it has a higher water extraction because it is located in a slightly higher elevation and thus nearer to the recharge areas and mountains. Due to the continuous groundwater extraction by SMWD's deep wells, the mountainous areas suffered bigger subsidence compared to the area where the deep wells are located. Soil type of Barangay Poktoy and the mountainous areas of Barangay Serna and Bonifacio are classified as limestone residue, which means soil compositions are made of weathered limestones. Groundwater highly exists on the unconsolidated materials like limestones. The mountainous areas are likely to be considered karst as conditions like limestone, ground characteristic, and Surigao City classified as type 2 climate with no definite dry season meets the criteria. Karst topography can store a considerable amount of groundwater supply. Serna 2, on the other hand, got the highest recorded subsidence as it is located far from the higher elevated areas and its groundwater extraction is continuous that the deep well extracted 116,370 cubic meters of groundwater resource. DINSAR processing approach was able to generate a terrain deformation map of Surigao City by using Sentinel-1A image pair. Over a single year span, April 2017 to April 2018, terrain deformation in Surigao City appears to be different on every barangays as both subsidence and uplift is seen. Majority of Surigao City appears to be subsiding, and specific barangays like Barangay Anomar is subsiding at alarming rate. Areas where SMWD's deep wells are located appear to be subsiding, and so is the adjacent areas where the connected underground basin is located. The study only used a single image pair due to the limitations of DINSAR approach on the quantity of satellite images it can process. The pandemic restricted travel, making acquisitions of deep well data more difficult. The unavailability of deep well data from local barrios restricted to focus the remaining areas that showed subsidence terrain deformation that can possibly correlate to deep well groundwater extraction. For further research, the following are recommended. It would be interesting to validate the results for this work by using other approaches as persistent scatterer interferometric synthetic aperture radar or the PSNSAR and the satellite-based augmentation system or the SBAS for more optimal results that won't consider the limitations of number of satellite images and the research interval for processing. Considering the broad application of terrain information, like how it is a factor to flood inundation, correlation to natural factors such as seismic movements, and the application of predictive analysis to produce deformation time series projection. Using external DEM like light detection and ranging, LiDAR, Aster Global, and compare its accuracy to freely available DEM. That would be all. Thank you for your attention.